60 miles. In 2 hours, 120 miles. Hi there. Now that we've looked at geometric sequences and I've been telling you how those model and follow an exponential pattern, let's jump in and look at some exponential functions. Okay, we're going to start by reviewing functions a little bit. Now remember that functions can be represented by verbal descriptions, that's with words, by algebraic equations, with tables, or with graphs. So let's review linear and quadratic functions. Now an example of a linear function would be you're driving to visit your best friend in Gulfport, and since you have a long drive ahead, you turn on your cruise control, and your cruise control keeps your car traveling at a constant rate of 60 miles per hour. So the algebraic equation that would represent this would be the function f of h equals 60h. Your distance, f of h, depends on your time, h, in hours. Now the numeric table that would help us represent this function is listed here, and you see that it's that constant rate of change. In 1 hour, 60 miles. In 2 hours, 120 miles. In 3 hours, 180. You're going up by 60. Each time you're increasing, every hour that passes, you're increasing by 60 miles. And we see when we look at the graph of the distance in miles traveled over time that it makes that linear function because it's that constant rate of change, going up by 60 every time. Now the next functions that we looked at that we've spent some time studying have been quadratic functions. Now those don't have that constant rate of change. And a good example is watching things drop because gravity pulls things down faster the closer it gets to the ground. So let's look at a verbal description of a quadratic function. You're observing the height of a ball as it's dropped from a 150-foot tall building. Because of the force of gravity, the more time that passes, the faster that ball travels. The ball does not travel at a constant speed, like your car on cruise control. The algebraic equation, the height of the ball, h, is a function of, or depends on, time t in seconds. The quadratic function can be represented by the equation h of t is equal to negative 16t squared plus 150. And so now when we look at this numeric table, we see that we don't have that constant rate of change in this one. Next, let's look at the graph of our quadratic function. And we see that it's not linear. Remember, it forms what we call a parabola, and this is half of a parabola. And we see that it's going faster and faster the closer that it gets to the ground. Okay, so we've done linear functions. We've done quadratic functions. Now, let's take a look at exponential functions. Okay. You are performing an experiment in your science class in which you start with 100 bacteria and the amount of bacteria doubles each hour. Let's look at a little graphic of this. Imagine that you've got this bacteria and here we show it doubling every hour. You can see why diseases can become such a problem because it doesn't take long when something is doubling every hour for it to grow to a really, really large amount. Okay, so let's look at a numeric table. Notice at 0 hours you started out with 100, and then it doubled to 200, and then 400, 800, 1600. So the rate of change is not constant, but it's doubling each time. And we see a graph here. We see that we started out with the 100, and then it doubles every hour. And you see by the 6th hour, you've got a lot of bacteria, and it's just going to continue to grow quickly. Okay, well, let's look at how we could write the algebraic equation for this exponential function. So we're going to go through the steps to write this equation. Okay, we're going to start by picking 2 points. And it's very helpful to use the y-intercept and the coordinate where x is 1. So the y-intercept is 0, 100. And then where x is 1, or in this case t is 1, it's 1, 200. Okay, so we're going to use 0, 100, and 1, 200. Okay, now this is the formula, the equation that we're going to use for an exponential function, this exponential equation. So we're going to substitute these coordinates into this, and we're going to solve for a and b. So I'm going to start with putting in 0 and 100. 0 for x, and 100 for y. Okay, so I get 100 equals a times b to the 0. Okay, now you see why I said use that y-intercept? What's anything to the 0 power? Anything to the 0 power is 1. So in this case, a is equal to 100. Okay, so I've got a. Now let me use this other point, and I'm going to substitute in a and the other point to find my b. Okay, so again, x and y here. So y is 200, so 200 equals, now I know what a is. A is 100. 100 times b to the first power. See, I'm just substituting in for the y, the a, and the x. 1 for the x, 100 for the a, 200 for the y. Now I can divide both sides by 100. B to the first is just b, so I get b equals 2. Now let's substitute a and b into the equation. Y equals ab to the x. So y equals a is 100, 100 times 2 to the x. And I've written the equation for that exponential function. Okay, let's practice with another one. The table and the graph below represent an exponential function. Okay? Write an equation for the exponential function. Well, again, I'm going to use these 2 points, my y-intercept, and where x is 1, 112. Okay, so remember, it's y equals a times b to the x. So I'm going to start out with that y-intercept of 0, 4, and I'm going to plug in 0 for x and 4 for y. So 4 equals a times b to the 0. Anything to the 0, this becomes 1. So that's 4 equals a, because that's just times 1. A times 1 is just a. Now I'm going to plug in a and x and y using this 112. 1 for x, 12 for y. So 12 for y equals a, I'm going to substitute 4 times b, and then for x, I'm going to substitute 1. B to the first is just b. So then I'm going to divide both sides by 4. And when I divide both sides by 4, I end up with b equals 3. Okay, so now I'm ready to write that exponential function. And I get y equals a, which is 4, times b, which is 3, to the x. Now, can you form a hypothesis relating the a term to one of the key features of the graph? Well, in this case, it was 4. What do you notice about your y-intercept? Your y-intercept is 4. Let's look at that last one that we did. My a ended up being 100. What was my y-intercept? My y-intercept was 100. So we should notice that it is the y-intercept. Okay, well, let's keep going. Can you form a hypothesis relating the b term to one of the key features? Well, in this case, notice b was 3. Okay, now if I look up here, what's happening here? What's my common ratio? 4/3 times what is 4? Well, 4/3 times 3 is 4. What about 4 to 12? 4 times 3, I'm going to use a raised dot so that it doesn't look like an X, is 12. 12 times 3 is 36. 36 times 3 is 108. Now, if we look back at the other one that we wrote the equation for, okay, I'm going back to the first one that we did, our b was 2. Look at that table. Notice, again, that's my common ratio. 100 times 2 is 200. Times 2 is 400. And you see it all the way down. So you should notice that the b term is the common ratio. Okay, the table below represents an exponential, let me get that where you can see it, represents an exponential function. Okay, so what I want you to do is take a minute and work this one on your own. go ahead and try to write the equation and then see if our, or not try to write, but do write the equation and see if our hypothesis holds true. So let's give that a try now. Okay, let's look at it together. Now, remember that we like to start with the y-intercept and where x is 1. So the two that I'm going to use, the 2 points, are 0, 2, and 1, 1. Okay, I'm going to substitute these in for y equals a times b to the x. Okay, 0 for x, 2 for y. Okay, so I get 2 equals a times b to the 0. Anything to the 0 is 1. A times 1 is a. So a is equal to 2. Now let's substitute in a, x, and y into it again so we can find our b. So 1 equals a is 2 times b to the first. Okay? B to the first is just b. I'll divide both sides by 2 and I get b equals 1/2 for that one. Okay, so, we're jumping ahead to the beat the test. All right, so let's see. Let's write that equation. We would have y equals, my a is 2, times my b is 1/2 to the x. Now, remember we said that the a was our y-intercept. Did that hold true? Yes, it is. We said that the b was 1/2. We said that that's our common ratio. Did that hold true? Are you multiplying by 1/2 each time? Yes, you are. 4 divided by 2 is 1/2. 4 times 1/2 is 2, which is the same thing as dividing by 2, by the way. Of course, we know that. 2 times 1/2 is 1. Okay? Now, this is an example where something is getting exponentially smaller. So it's nice when this happens if there is a disease and we find a cure and we can get that disease wiped out quickly. So, did our hypothesis hold true for this equation? Yes. Yes, it did. Okay, now, great job working with me on those. Now let's pull it together on this Beat the Test. Okay, so we have our Beat the Test here. We're going to match the graphs below with the following functions. Okay, now what have we discovered? We've discovered that that a term is our y-intercept and that whatever's being raised to the x is our common difference. Okay, so if there's no term here multiplied by that number raised to the x, then there's an understood 1 there. So I could think of this as 1 times 3 to the x. Okay, I could think of this one as -1 times 3 to the x. Okay, so just because there's not a number there, don't think that there's not a y-intercept. Okay, so here I have a y-intercept of 1 and a common ratio of 3. Okay, I'm looking for a y-intercept of 1. There's a y-intercept of -1. Here's a y-intercept of 1. Okay, do we have a common ratio of 3? We have 0, 1. Let's look at that next point. That next point is 1, 3. So I went from 1 to 3. So should the next one be 2, 6? 2, 9? Yes, it is, because 3 times 3 gives me 9. So this one does match up to that. 1 times 3 to the x, or just 3 to the x. So f of x equals 3 to the x. Okay, now in this one, I'm looking for a y-intercept of 2 and a common ratio of 3. Okay, where is my y-intercept of 2? I see it right here. Okay, so that is 0, 2. So if the common ratio is 3, then the next term should be 1, 6. So I look at 1. Yep, 1, 6. Now when I multiply 6 by 3, I would be all the way up here at 18, which it looks like it's going to be. So if you went backwards, you would take 2 and divide it by 3 and get 2/3, which looks about where that is. So it looks like my y values are going up by that common ratio of 3. So we're going to put f of x is equal to 2 times 3 to the x. Now again, I could just find these by looking at the y-intercepts since they all have different y-intercepts, but I do want us to at least check a couple of points to make sure we see that common ratio of 3. All right, so here I'm looking for a y-intercept of -1, which there it's -2, should be this one, -1. So I want to see, is my next point going to be -1 times 3, which is -3? I would be at 1, -3. Sure enough, there it is. -3 times 3 is going to be -9. So is it 2 at -9? Yep, right there it is. Okay, so that one goes here. -3 to the x. F of x equals -3 to the x. Finally, the last one should be f of x equals -2 times 3 to the x. I'm looking here. Do I have a y-intercept of -2? Yes, I do. Do I have a common ratio of 3? -2 times 3 is -6. Let's see, is that where that next point crosses? Yep, it sure does. -6 times 3 is -18, so I can't check that other one. But I could come here and go backwards and take and divide by -3. -2 divided by -3 would be -2/3, which, yep, it looks like that's right about where that's hitting. Okay, so we're going to put f of x equals -2 times 3 to the x. And again, I could have just found my intercepts, but I did want us to look for that common ratio as well. All right, great job working with me on those exponentials. So come back again in the next section. We're going to start looking at graphs of exponentials. Going to have a lot of fun with that. So I hope I'll see you around. In the meantime, have a fabulous day. I'll see you soon.